Good afternoon, everyone. So, this is an extra interactive session that we are going to have today. Yeah, as you all know, this is NPTEL Experimental Physics second module course. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am PMRF Research Scholar Mrinalini from School of Physics, University of Hyderabad. And we already have finished 12 weeks interactive sessions where we were discussing the little bit of theories that were discussed in that week's lecture, and then we were mainly focusing on a lot of numerical problems to solve so that you guys can uh, attempt your assignments and then the exam. So this is the extra session. Here I want to discuss some information about the related to your exam, that the hall ticket I think is not yet released. So the centers, like someone had asked about the center, we scholars don't, we TAs don't have idea about these things. You will get proper email or some other information via through NPTEL itself. But here I would like to today tell you some information which includes, yeah, we'll see, and then we'll have a revision of all the topics that we had covered in this NPTEL Experimental Physics 2 module. Yeah, so let's start. So first, this is very important because in one of the classes also, one of the interactive sessions, one student had asked that what will we be able to use calculators. So this is the information that email had come from NPTEL regarding this, where it was clearly mentioned that physical calculators will not be allowed inside the exam hall. So this is specifically for this course, because there are different courses. Some are pen paper based and many of them are online computer based. So for our this experimental physics course, the exam will be computer based or online, and thus the physical calculators will not be allowed. Any sort of calculators will not be allowed. Only you will get in the computer system itself online calculator option will be there, which looks something like this. Okay, now we'll see little bit how to use this. In fact, you should, before going for your exam, you should use this link, and in this link you will get this calculator. You should try it out because its working is little different than the physical calculator that we use. So like in physical calculator, we take first uh, uh, um, the sign function, and then you give it the value, and then it tells you the answer. Here it's slightly different. That's why, so that you don't get wasted in the final exam, thus I think it's better that you first try out these calculators. Okay, I think let's do this here. um, so let's try out this link. So this is how, if you will use this link given in here, this is the link. Okay, when you will use this link, you will get a page like this. Here this is, so this is the same calculator that you will be getting in your exam. So in this calculator, let's see how, as I said, its little functioning is different. Like in normal physical calculator, we first press the function that we want, and then we in those brackets we enter the values that we want. But here it's different. As you saw that when I click sign, already it's taking 0 as the input. So that is how, what I was telling, it's different. First of all, you won't be getting keyboards there, so you will have a mouse, and using that mouse only you have to do everything, be it selecting the options or be it using this clicking these numbers on this online calculator. So like if I want to take sine of 90, say, so notice that we have two options here for angle. One is degree, another is radian. So like be cautious that which one is kept selected here. So if, say if it's degree, I'll just maximize it a little bit. I think this is better. Yeah. So if we have kept selected degree, then all the angle value that we are inputting, it will be in degrees. So like if I want sine of 90 degree, so I'll click 90 and then I'll take sine. So I'll get, don't get confused seeing here, okay, this is sine only. So sine of, this means degree, okay. So sine of 90 degrees is 1, which we know is correct. So this is what you have to keep in mind, and you should try it out yourself, that here if you are taking, again as we did with sine, first we have to put the values for which we want, on which we want our function to act, be it cube root, square root, modulus. First you have to put the values and then you have to select the function. Like if I want cube root of 8, first I'll input 8 by clicking here and then I'll take the function, so I'll get the answer 2. Which, why I'm saying you practice it first, because it's different than physical calculator. Physical calculator, we first take the function, then we in bracket we put our values for which we want that function to act on, right? So that's why this is little different, and if you will attempt directly in the exam this kind of slight variation, you will be confused as well, and it will take your time, in fact eat up your time. So that's why this link is, you must have got an email from NPTEL. From there itself I have taken this link. I think the same kind of calculator we get in GATE exam also, that is also an online exam. But in case if some of you have not had experience of online exams before, so of course I'll share this PPT, and from there you can just copy this link and open this calculator and try out yourself how to do various functions using this, right? I think most of the whatever you will need, everything is there, sine, cos, this. So yeah, so I think if this is clear, the usage of calculator. Apart from this, the assignments pretty much covered everything that can come from the experiments. And yeah, so of course you don't have experiment lab exam where you have to perform these things only. That's why the assignment questions will be sufficient, because all the kind of questions that can be asked related to those experiments or the theory behind them, all those things have been covered in those kind of assignments. And also the numerical problem that we were discussing in every week's interactive session, so those were the questions that we had taken from previous year when the same course was conducted. That time the assignment questions which were given to the students. So this time when we were discussing those questions itself. So one, you have this year's assignments, which solutions, for whom the solutions you have already obtained now, and also you have these extra that we were discussing every interactive session. So I think if you do all these questions, then it's more than enough for you to attempt your exam. And then the use of calculator, you have to be clear, because it will be very important. There will be some questions where you won't need calculator, but there will definitely be, I think at least half of the questions where you would need these, to do some kind of calculations, for which you will be getting this kind of scientific calculator. Okay, so this is done. Then okay, so this was what I wanted to tell you. Right now we don't have much information apart from this. So if you guys have any question, you can ask related to exam information. I think the whole admit card we will be getting soon, but right now the date and these things information is not available to us also. So yeah, you will have to wait. It is somewhere in April or May, because there are so many NPTEL courses, so this will also be scheduled some particular time. So if there is no more queries regarding this, then I think what we can do today is, we have already done extensively lot of numerical problems based on all the topics, but let's just revise the things that we have discussed. It's like a summary we'll do today in remaining time, and then so that our things get refreshed, and if something is still doubt, you can ask. I think this is one way we can utilize today's time. So this experimental physics course, I think in the introductory class also we had discussed that last time experimental physics 1 course we were talking about more electronics part of in an electronics lab. What we do, we have resistors, we have inductors, capacitors, how do we make circuits, how do we measure capacitance when capacitors are in series, parallel. We had, before doing all these experiments, one thing we were, as the professor was also discussing, which is very important. In fact, when you must remember that whenever in school level or college level also, whenever we write our records, first we write the theory behind that, because knowing the theory is very important, and how we get the formula and what is the working formula for that experiment, and then we move on to how to perform that experiment, and then what else becomes important is what all the precautions we have to keep in mind. So that's what we had discussed in experimental physics module 1 also, and then we revised in second module, first week interactive session as well, that when we are going to perform any experiment in a lab, we need to know the theory behind it, the working formula, what are the parameters we have to find out, what is the final result we want to calculate, then what precautions we have to keep in mind, what are the different sources of errors in these measurements. Then very important thing that we were discussing about the significant figures, we'll discuss again this little later. And so how to interpret those results. If you take care of these things, then your experiment will go correct. Okay, so in this second module, so what we are discussing is, from now we are discussing about optics lab. What are the experiments that we can do, or we generally do in an optics lab at this graduation level or school level. So, and what are the different kind of components that we see in optics lab, like different light sources, like we have sodium light, right, or sodium light which is like monochromatic. Then yeah, so light source also are like monochromatic. And then we have white light source, which has 7 different components. We know now all these things. So in monochromatic, sodium, then white light. Usually sodium is widely used in labs actually, and we know it has D1, D2, two very close wavelength also, but still we can call it monochromatic for our purpose. It looks like yellowish in nature. Then we have white light, for which we use mercury source, helium source, and so on. Then we have different kind of mirrors, concave mirrors, convex mirrors, plane mirrors. These we had discussed in well detail, which again we'll revise today. Then beam splitters, which are basically like kind of they look like mirror, but they have been polished in such a way that some part of it goes transmits and some part of it is reflected. So the beam is actually splitting into two, as you can see. Some of it is getting transmitted, some of it is getting reflected. So those were beam splitters. Then prism, again this is a prism which is used for dispersing a white light into its various components. And then we had discussed angle of prism, angle of deviation, what is the condition for angle of minimum deviation. So this is very important component found in an optics lab. Then grating. After we had discussed single slit, double slit diffraction, then multiple slit diffraction. Under that we had understood grating. We have 2 types of grating: transmission grating, reflection grating. Then spectrometer. This is what we call a spectrometer. Sorry, wait. This is a spectrometer, very important. At the center we keep our usually prism, And then from collimator side, what is okay, wait. From collimator side, we get the incident light which falls on the prism, and prism, or we may be doing some experiment with a grating. Then this is some stand in which we will keep our grating. So some kind of optical component through which when light interacts, what we get interference or diffraction pattern, we see that this side. So this is spectrometer, and then here is a scale through which we measure what is the change, what is the angle variation that is happening. Spectrometer is another component. Then telescope, here through which we will see the pattern because we need to magnify it. Telescope or microscope, etc. So these are the basic components that we have been, if you keep on read, these are the basic things, tools that we discussed experiments based on them, and these were the tools we were using to do various kind of experiment. Yeah, so the things that we were doing, that we discussed, were like reflection phenomena, refraction, the laws related with reflection, refraction, what are the conditions, and what are the different way light interacts, and then we get interference pattern, we get diffraction phenomena. There is something known as polarization that we discussed in so much detail, that unpolarized light, polarized light. Then quantum physics related experiments we did in previous week, where we discussed Rydberg constant experiment, Frank Hertz experiment, which are like these are the experiments which were done when this field of quantum physics was being explored, and there were scientists like Planck and Einstein who were giving, or Schrodinger, who were giving some theories. And then in physics or in science, it's always important that we, for proving those theories, which until proved we call them hypotheses. So until we conduct some experiment, we get some experimental proof, we don't accept that those hypotheses. So these were some very important experiments that solidified the hypothesis regarding quantum physics that was developing during those times. So these were the things that we had discussed, like main heading, under which we had discussed various experiments and a lot of theories related to that. Like, okay, so this is very important. This is very important whenever we are doing any experiment in lab. Again, so we'll have a revision because this is very important part, which we tend to forget later also, when we leave the study kind of thing and be in like higher studies or research, that whenever we are conducting any experiment, it's very important what are the digits, decimal digits we are taking, what is the magnitude, what is the error in it. And this is what we had started discussing, that there's something called accuracy, something called precision. Just to recall, accuracy we define, it's a measure of how close the measured value is to the true value. Like for example, if the gravity value we all know is 9.8 meters per second square, and I'm performing some experiment in lab and I'm getting the value as 9.7 meter per second square or 9.9 meter per second square, then we'll say this value is closer to the true value. But if some other person is conducting an experiment, say some person B is conducting an experiment, and he or she is getting the values as 7.8 or 8.999 meter per second square. Now again, what precision, this is going to a lot of decimal digits, means it's giving kind of very resolved value, that it's precision tells us to what resolution or limit the quantity is measured. So it's giving up to third decimal digit, that's good, it's very precise, but it's far away from the actual value, so I cannot call it accurate, right? It's very precise, okay, but it's far from the true value, it's not accurate. I'll call this accurate, but not this. So this is the difference we have to keep in mind, where we should focus more on accuracy, where we should focus more on precision. And we cannot just this again, what I want to say, we cannot just if I have some values like 3.0 and I divide the say 7.0 divided by 3.0, so calculator will give me lot of decimal digits, but reporting all that doesn't make sense. So the values when I'm reporting after some mathematical operation depends on what was the number of significant figures or what were the number of decimal digits in those values. That again to recall. Yeah, so before that, whenever we perform any experiment or we do any sort of measurement, there are different kind of errors which may happen knowingly, unknowingly. Sometimes it's like personal error. The person may, um, due to parallax, that sometimes I'm seeing a scale. Say, this is a scale. I'm measuring something, it goes like this. If I'm seeing from this side, I may see it's crossing this line. If I'm seeing from this side, then I may see that it's still not to reach this particular line. So that happens parallax. That's why we are supposed to keep it exactly um, perpendicular and then take reading. So this is personal error, but there are some other kind of errors may happen, and those various sources: instrumental error or imperfection in experimental technique. So like zero error, when we were discussing about vernier caliper also, maybe the main scale and vernier scale, their zeros are not matching, then positive or negative zero error may happen. Then what should we take care or keep in mind to eradicate these kind of errors? That also is important. So these were the errors that we had discussed. Then there, yeah, so we had discussed what type of errors we, what type means these are different sources of errors. Then which are the different way through which we report the error. So usually when it's important to tell, maybe in day-to-day life we don't talk about errors, right? Like if I'm going, I'm just telling some random for some random reason, not that accuracy is needed. So I may tell, okay, my height is around 5 feet and my weight is around 65 kgs. So there people know, okay, it may be 65, it may be 65 point something, or it may be 64. So it's okay. But if I'm weighing some sample, aware for every gram, the something like gold, right? Gold we all know in day-to-day life, it's very important. For every 1 gram we are paying some huge amount. So there I cannot say just 65 or something approximately. There we measure and then we give some error value, that okay, we have measured it is 5 gram. Not happens on gold, but sometime it happens, we may not be getting something accurate. So we tell this 0.1 gram, there is some error. So it could be 5.5 gram, or it could be 4.9 gram, sorry, it could be 5.1 gram, or it could be 4.9 gram. So when we write something like this, means it could be this, it could be this. So we acknowledge that there could be some error in it depending on the way we measured it. Then this is what's about. There are three ways we report an error: absolute error, where it's always positive, and we magnitude of difference between individual measurement and true value of the quantity. Like if the true value is 9.8 meter per second square for acceleration due to gravity, and this I measure in some experiment 9.7, then absolute error I will take their difference and then I'll take mod. So the, as I was saying, we'll report the value of acceleration in our measurement came out to be, I got it as 9.7 and then plus minus 0.1 meter per second square. So this way we will be reporting the value. So it could be 9.8, it could be 9.6. Relative error, this is how we, this error divided by the actual value, this is how we denote relative error. In percentage we multiply it by 100. So we tell there is 2% error or 1% error in the reading. So these are the three different ways. Then we discuss about oscillation. This is also the topic that was discussed in module 1, so we don't need to discuss more. But we had seen there are different kind of periodic motions around us that we see, be it the swing, be it some clock, hand of a clock. So these are all periodic motion which repeats themselves. That we had, there's a simple harmonic motion which is specific kind of these periodic motions, where the restoring force is directly proportional to the displacement of body and its direction is always towards the mean position, as you can see for pendulum or spring mass system. So we had discussed these things, that there is undamped, damped, and heavily damped kind of conditions or cases. Then yeah, so significant figures, as I was saying, the concept of significant figures becomes very important when we are reporting some value after doing some measurement or taking some data from some instrument. So significant figures include the reliable digits plus first uncertain digit, and it indicates the precision of measurement, which depends on the least count of measuring instrument. And these were various conditions. All these things we have discussed in very much detail in our first session. So please, if you have any doubt, in fact I think I have shared one chapter of class 12 NCERT physics book, where all these things with examples are given very nicely. I am sure you won't have any doubt after referring that. But in first interactive session class also we had discussed these things with example, that there are certain rules we need to keep in mind so that everyone's concept of significant figure remains same, uniform throughout the universe, throughout the world at least. Okay, and then it included a lot of things about trailing zeros and the zeros before decimals. So I mean, if you keep in mind these few rules, then you won't face any problem in understanding what is the significant figure in this particular number. And this is what I was telling about. If we are performing some kind of arithmetic operation, then if in phone, if I do this calculation that I want to find out density, okay, wait a second, yeah, if I want to find out density, we know it's mass upon volume, right? And this mass is 4.237 gram. There are four significant figures, and then the volume is 2.51 centimeter cube. Here there are three significant figures. So density, if I'll do this in any calculator, physical calculator or online calculator, depending on their capacity, how much up to which decimal digit or up to which digit they can show on the display, they will give me values like this. Maybe it's irrational number, it's not going to stop, it seems. So if I use some calculator, I'll get a value like this. They won't be ending, or it will be up to this much decimal digit. But is it the correct way to show something for division of these two numbers, where the first numerator has four significant figures and the denominator has three significant figures? So no, we cannot show something like this. It questions the accuracy, the precision, that if the instrument that I used, based on that instrument, I could only get up to 3 decimal digit, and the volume, whatever instrument I used, it gave me the significant digit for volume up to only 2 decimal digit and overall 3 significant figure, then the answer cannot be this precise. It doesn't make sense. The calculator may be giving, it doesn't know what we are doing. It's just doing the maths, but we have to use our mind and try to analyze the result. As I was saying, analyzing the result is very important part of doing experiments. So we have to analyze this, that this much precision cannot happen and is not making sense. So we have to restrict. Although we are getting answer from calculators up to 11 decimal digit places, but we have to keep in mind this rule, that in multiplication or division, the final result should retain as many significant figures as there are in the original number, and that original number which has the least significant figure. So these are the original numbers, and the one with least significant figure is this. So our answer will have 3 significant figures. That's it. Which makes sense, because one of the instruments only could give up to 2 decimal digit accuracy or precision. So our final answer also should be incompatible with that. So this is the rule. That's why this makes sense and it's so important. Similar way, this was about multiplication and division. Same way we had discussed that for addition or subtraction. Then here also you see the number of decimal digits. Number of digits of decimal are different, and total number of significant figures also are different. Then in this case, what we have to do, so for addition or subtraction, what we keep in mind is the number of digits after decimal place should be the minimum number with the least decimal place. So here with the least decimal place is this. So my final answer will also have uh, the total whatever I'm getting, but the decimal will not go. Okay, let me just do this. So this is like 436.32, right? And 227.2. There's nothing here. Then 0.301. If I'll add, it will be 1, this will be 2, this will be 8, 13, 6, 6, this much gram. But will it be the correct way to represent? No. So I have a number which I am adding whose decimal digit is only going up to first decimal digit. So my final answer cannot have more accuracy than, because here we don't know what is the next two digit. The instrument whichever I use to measure this particular weight, it could not give more than the first decimal digit. So how I am sure about these two, the hundredth and thousandth decimal digit in the final answer? I cannot be. That's why we restrict it to first decimal digit. Our answer, this way of writing the answer will be correct. So this is the whole concept of understanding significant figures. Then here comes rounding off as well. That like in this case itself, my answer came out to be 821. Now, as I said, the right way of writing the answer will be restricting the answer to first decimal digit. So I cannot simply discard the other two digits. I have to consider them, and I have to do something known as rounding off, which I'm sure you all know, which we keep doing in our daily life. If some bill is like 39.5 rupees, we have some cash, we'll give 40 rupees. We don't have 50 paisa, or even if it's 39, okay fine, we'll give 40 rupees something. So we do round off. We'll not round it off to 30, right? We'll round it off to 40, which is the nearer. Same way what we do here, if it's 8 to 1, then 1, if I round it off, I want to restrict it to second decimal digit. These will remain as it is, the digits before the decimal. The next will be, I'll round it off 1, then 1, if it is 1, then I can keep it 2. If it's more than 5, then it will increase the value of 2 to 3. So here it will remain 2. Now, if I'm again rounding it off to, like here I have to round it off to first decimal place, right? So I further round it off. And because this is 2, so this will remain 8, and thus my final answer will remain this gram. So when we take care of these rules for doing the arithmetic and significant figure and number of decimal digits, then this concept of rounding off also we need to keep in mind. This was also something we had discussed, and what are the rules regarding it. So those things we had discussed in module 1 also last year, if you want to check. And this year also in first 2 interactive sessions we had discussed these things thoroughly. And also again there are a lot of numerical problems related to that, so I'm sure you won't have any doubt, but still if you have anything you can ask me now. Okay, so meanwhile, okay, let's move on. Then after that, after discussing those important things that we have to keep in mind while performing experiments, we moved on to the components, discussing about the components that we find in optics lab, which are like mirrors, plane mirrors, concave mirrors, convex mirrors. Then we understood what do we mean by reflection, that we encounter in day-to-day life everywhere, light reflecting from somewhere, and then what are the laws it follows. There are certain laws that the light follows, and then only we call it reflection, that angle of incidence is equal to angle of reflection, and the incident light, reflected light, normal, all are in the same plane and they meet at a common point. These are the things that we talk about when we talk about laws of reflection. And then from where we measure this incidence angle, so the normal to this reflecting surface, this normal, what angle it makes from the incident light, that is called angle of incidence, and not this other thing. This is not angle of incidence. Angle of incidence is always measured from the normal to the reflecting surface. This also should be kept in mind. Then we started discussing about these curved mirrors and curved lenses, that we have concave mirrors. Okay, and so concave mirror is something like this. It's part of a very huge sphere. We cut a small part and then what we get is something like this. Then if I'm polishing this small cut parts of sphere from outside, then the inside becomes reflecting. And in this situation, depending on at what distance the object is from this concave mirror, the kind of image that I get also changes. Like if I'm keeping it between C, center of curvature, and focus. So if I said it's this concave mirror we get after cutting a small piece of this something spherical. So it where its two diameter meet, that is center of curvature, and half of it is focus. Somewhere here is center of curvature, somewhere half of it is focus, and all the lights coming parallel passes from focus, all the lights coming through focus, I mean in getting incident through focus, goes out parallel. And then if so, this is C, this is F. If our object is between these two, then the image that we'll get, it will be real, it will be inverted, and it will be larger than the original object. Then if object is at focus, we'll get no image. Why? Because as I said, the light passing through the focus will go out and become parallel. That means it won't be focusing anywhere, so we won't be getting any image, as you can see here. If the object is kept between C and F, then the object that we are getting will be larger, real, and inverted. Same way, these other things we had discussed, that depending on the position in front of concave mirrors for the object, the image position, image size changes. So depending on this property, we have various applications, like we use it, dentists use it to check our in our mouth, or we use it for shaving mirror, basically to magnify, because we are going to keep it closer to our face. So there we can use. So we had discussed various uses of concave mirrors and convex mirrors. Convex mirrors mostly we see always it's used for side mirrors in our two-wheelers or four-wheelers, because what it happens is it shrinks it gives, so a very important thing is why we use convex mirrors. It doesn't give us of course the original size, but it helps us. If I'm seeing at the side mirror, I'm getting in a small mirror, I'm able to see a wide view of the traffic behind me. And also the important thing is, since the image formed is virtual, that's why the image is erect. So unlike concave mirror where the image was going upside down, in using convex mirror the image I am getting is erect. So I am not seeing a vehicle coming upside down, I am seeing it erect. That's why it's very useful in side mirrors or similar kind of applications. Then moving on from reflection, we had discussed refraction, that there are, when we have different medium interface, like this is air, then this is glass or some other kind of material, and light incident on this, instead of reflecting, it passes through that. Then what are the different laws that are being followed? So that comes under law of refraction, and based on this we had understood the concept of refractive index, that air has refractive index of 1, and any material which has refractive index more than 1 means the light will slow down when it will be traveling through that medium. Like here for this case, this is air we are saying, right? So refractive index here will be 1. Refractive index of glass is more than refractive index of air, so it's more than 1, so 1.5 depending on what type of glass we are using. So light, when it's coming here, instead of reflecting, it's passing through it, but it bends towards the normal. Why? Because the speed of light in this high refractive index material, it slows down, and that's why it's come towards the normal. So this is what happens when we talk about refraction, and that's why we see in a glass, if there is some water and I have kept some pen, pencil, anything, when I'll see some bending. I won't see it the way it should be. But although the object is not bending, of course it's not bending. If when you take it out, the stick will still be straight. but when you see side view, you'll see it's bending. Why? Because of refraction. The light that is coming out, this is happening to it. So these are the things actually which answers the various kind of things that we see around us. It's because it's very bizarre if we'll see that something is not bent, but when I'm keeping it in a water or in some way, some glass, why is it looking bending? Because refraction is happening there. Light is getting refracted there. So these are the laws which seems very obvious, but until they were, explained to us, we didn't know the things happening. Then, yeah, so we had started discussing for these concave mirror, for these convex mirrors or concave convex lenses, we had started to see how to find out their focal length. So this was the first experiment, focal length of concave mirror, and this is the lens maker mirror formula that we use. Yeah, so please keep in mind again, these things of course we have discussed in detail, but I'm emphasizing, keep in mind the sign convention. We had discussed sign convention in detail, that when the object is on which side and image is on another side, or up or down depending on where the focus of the mirror or lens is, based on that every time we were talking about if u and v are positive or negative, or f is positive or negative. This is the basic formula, but depending on u is positive or negative, our formula was changing little bit. And if you remember, whenever we were solving questions, the first thing I was telling you, and I was doing also if you watch those videos, as soon as we read the question, we were making the diagram, that okay, this is a concave mirror, that means it could be something like this. If it is a convex mirror, then it will be something like this. First we start making this. When we make the figures, things become clear. Otherwise it may get confusing. Then we were making, okay, what is the distance of the object, depending on it we were seeing, okay, for this focal length is here, object will be here, so it will be negative, image will be from the same side, so v will also be negative. Whereas for convex mirror, focal length, focus is here, object is here, so it will be positive. So as soon as you read the question, you start writing the values given, and you start especially making these kind of figures. You don't need to make like perfect circle using compass or anything, right? It's just basically for you, so that the picture the question is posing is clear to you. Then it's very easy to just use the formula and get the answer. But if you don't make these pictures, things get a little tricky, especially when you have to deal something like these sign conventions, right? Sometimes it's positive, sometimes it's depending sometimes it's positive, sometimes it's negative, depending on where is its position. So this is, I would suggest you to do, and we, while discussing numericals, we were following this, so I would suggest you also do the same. Okay. And then, yeah, this was we were using this graphical method to find out the focal length of the mirror. Then this was for convex mirror, where we needed another convex lens to do this, because the image won't be formed. Then we got introduced to spectrometer. I was saying spectrometer is something like this. One side the light is incident, then we keep some optical tool here, like grating, be it transmission grating, be it reflection grating, and then we had a prism. So the light coming through this collimator, we use the collimator, it has a lot of functionalities in it, so that we get very small beam of light coming through it, and then whatever happens after interaction, the light goes through this and we observe. So these were different parts of a spectrometer which we had discussed. And then we moved on to understand prism, which is made up of some kind of glass. Then white light coming through it gets dispersed. Why? Because refractive index is dependent on, refractive index of any object is function of wavelength. So for different light, the wavelength is different, refractive index is different, and that's why the angle by which it deviates becomes different, and ultimately they all split out. If you want to again get the white light, then you may keep inverted like this, so that all the splitted light will come here, and then ultimately you will get white light again. So these are very interesting, lot of experiments which are inspired by what we see around, and then we try to copy or repeat them in our labs limits, but we're able to do these. These are very interesting experiments. So reflection in triangular prism, which we had understood, there's something called dispersion phenomena, which is the process of white light incident on one side of prism splits into component colors when passed through prism. This happens because different colors of light have different wavelengths, and the prism material's index of reflection varies with the wavelength. So when we were discussing prism, we were discussing about angle of prism. Okay. So this is a prism. It has all sides not transparent. Apart from these two sides, or all other sides are opaque. So only these two sides are transparent, and light, when we conduct experiment, we make incident the light on one of the transparent surface, and it comes out from another transparent surface, and the angle between these two surface is called angle of prism. And what was the angle of minimum deviation? So as we were talking about light incident, it will, if there is no prism, the light will travel straight, but if I am keeping a prism, it will refract, it will go towards the normal, and again this is another interface, so again refraction will happen here and the light will come out. So instead of going here, now it's coming out here. So the deviation in the path, we were calling it minimum deviation, angle of deviation. And then we discussed that minimum deviation happens when the light is going parallel to the base, and when these two refractive angles are same. This we had discussed again, in a lot of detail, and also we had derived the formula for this situation. And this was the experiment based on angle of how to find out angle of prism using spectrometer and keeping a prism there. Then we had got the formula for dispersive power, resolution, and then we moved on to discussing interference phenomena. That when it happens when we have coherent sources, very important condition, and so superposition of waves happen when lights are incident and their amplitudes are added or subtracted, and thus we get the bright dark pattern. So the important condition is we need two coherent lights to interfere. Coherent means they have same frequency and wavelength, their amplitude may be same or different, but their phase has to be same, or the phase has to have some constant phase difference throughout. Then only we see these interference pattern. This is like with monochromatic light, we'll get this bright dark, bright dark. When we are using white light, we will be getting these different components. Then we had discussed Young's double slit experiment, that it tells us about, this is the experiment that told how we can get a coherent source, because if I use two independent source, it's difficult for them to be coherent. But if I am using one source like here, and I'm keeping a screen in front of it with two small holes, such that we had discussed this Huygens principle. This is that every source, every point on a wavefront, primary wavefront, acts as secondary wavefront, every point. Okay, so based on this, whatever point is coming here, it's again giving this as if like birth to new wave. So these waves, when they'll come out, they will be coherent with each other because their source was same. So these lights, when they interact at some point, we'll get this interference pattern. This was Young's double slit experiment. And there are different kind of prism. We had discussed different kind of mirrors, different kind of prism, which gives us a interference pattern. Then what is the path difference we'll get, how we'll calculate the phase difference, depending on it, at what distance will the distance from this zeroth position, at what distance from the zeroth position we'll get bright or dark. These all conditions we had derived and we had discussed. And this is amplitude splitting interference we had discussed. Then measurement of wavelength of monochromatic light by Fresnel's biprism, very important, we were discussing. Yeah, after that we were discussing about Newton's ring experiment. So till now we were discussing, we were getting linear pattern of dark bright, but with Newton's ring experiment we were able to get circular dark bright pattern, like you can see here. Instead of linear, we were getting circular patterns. That's why they were called rings. These were the theories and experiment behind them. Then we had discussed about Michelson interferometer, where after the light from the same source, it gets splitted using this beam splitter, and when they combine, because they have some path difference between them, that's why we get some ring kind of pattern. Again, what will be the condition for uh, brightness, what will be the condition for destructive interference, the condition we found out from this, and what should be the thickness of this plate depending on if what position we want to get darkness and brightness. Then we were discussing about diffraction, another phenomena. Yeah, this is what I was telling, Huygens principle. Each point on a wavefront is regarded as new source of waves, and that's why in Young's double slit experiment also we were seeing that one source giving rise to two sources which were coherent. Then we were discussing two types of diffraction, Fresnel diffraction and Fraunhofer. So the diffraction where either source or screen both are at finite distance with respect to the screen or aperture or obstacle, that type of situation we call Fresnel diffraction. And when source and screen or both are at infinite distance, then we call it Fraunhofer diffraction. These are the two type of diffractions. And depending on Fraunhofer diffraction, these were the situations. And we had discussed diffraction even further, that for diffraction to happen, the wavelength of the light that we are using, its wavelength should be proportional to the size of aperture or size of barrier or size of this thing. Otherwise, the light won't bend. Like it's very wide, so light is, we are seeing very small diffraction from here. But if the wavelength is comparable to the size of this gap, then we'll see good diffraction. This was then we had seen what is the pattern we'll see through single slit diffraction. We'll see something like this. We had got the conditions for it. Then we saw what will happen when we use double slit. In here there are two things happening, diffraction as well as interference, because there are two sources of light. Because of this, see, this is diffraction, this is interference, and when they combine we get something like this. So all these in details, of course, we have discussed. I'm just revising. If you have any note, you can ask. Then we were discussing about Fresnel diffraction, where we get Fresnel zones. This is again very interesting and very important, because what we see is we get circular wavefront here, and if we divide it into different half period zones, then from one zone will get amplitude added, the next zone will give the amplitude which will be subtracted, right? And depending on this, we have divided the zone in odd number or even number, we will get this, the amplitude will be like this. But if we want to use it as convex lens, what we do, so we had different zones. If I cover this and then I cover this, then the light coming from here which was getting subtracted, now it's not coming. Light coming from here which was getting subtracted, now I have blocked this, it's not coming. So all the lights are coming from every second zone, they are getting added. So basically this is acting as a amplitude is completely increasing. That means it's acting as a convex lens. This we had discussed detail later as well. These were the experiments. And as we discussed single slit, double slit, same way we have multiple slit, which is like grating, through which we get patterns like this if monochromatic light is used, and this if we are using white light. This is how it looks. And Yeah, after this we have started discussing about polarization, that we have such kind of material through which the light, when travels in different direction, its velocity changes. Those are anisotropic medium, and when the light traveling in any direction in that material but its velocity remains same, those materials are called isotropic. So we have an isotropic medium like calcite and quartz. So we had discussed what kind of anisotropy they show. Uniaxial anisotropy, usually these two show, but one shows positive, another shows negative. Then we get something known as ordinary ray, O ray, and extraordinary ray, which is E ray. So these materials are called birefringent. We get two rays out of them. This also has various applications that we had discussed. Yeah, so O ray gives sigma polarized, E ray gives phi polarized. Their velocity depends on the direction in which they are moving. Then using these birefringent material, we can make something as Nicol prism. Nicol prism we can use. So how we are making? Just a quick recap. This is one calcite material, say, and another, and we are pasting it using Canada balsam because it's kind of transparent for the light. So when we put them like this, the O ray is completely rejected and E ray reaches outside, so which is completely polarized. Earlier it was unpolarized, means the electric field component of the light was varying in one direction, but now its variation is only, I mean, earlier its variation was in all the possible directions. Now it's restricted to one direction. That means we have made it polarized. So this is the application of these kind of anisotropic crystals to make something known as Nicol prism, which is actually, we call it polarizer. That we used it to change an unpolarized light to polarized light, and then we use the same Nicol prism with respect to, depending on, with respect to polarizer what is its angle, it becomes analyzer. Like we use it to analyze if the light that we are getting, it's polarized or not. If it's not polarized, then whatever angle I'll change for of analyzer with respect to polarizer, I'll still get some light outside, because the wave vector, electric field wave vector, is propagating in all directions. But if it's polarized, then the condition will be different. That also we have discussed. Then these are different prisms that depending on the way we are pasting these two prisms together, the O ray, E ray that we get outside, that changes. And we have discussed Wollaston prism. This is also something similar. Here the optics axis is perpendicular to this direction, and that's why the here what it's, even if it's coming in same direction, its velocity changes. Then yeah, so we have discussed, depending on how we are using these polarizers, we can get something known as retarders, a quarter wave plate, half wave plate, or full wave plate out of those. The next thing we had discussed was verification of Malus law. So we started talking about how light is an electromagnetic wave. It has electric field and magnetic field components, and since electric field components magnitude is significantly higher than magnetic field strength, that's why we usually even ignore this H value and we only talk about electric field components variation when we are talking about polarized or unpolarized light. When we are talking about for light, the E field and magnetic field are perpendicular to each other as well as perpendicular to the direction of propagation. Then, so this is right now unpolarized, and we have various ways through which we make it polarized. So that, yeah, and when we have after polarizer, we put an analyzer, and depending on the angle between the polarizer and analyzer, this is the law. This is the angle between polarizer and analyzer, and depending on the angle between them, we get the intensity outside. This is the law, and then this is Brewster's law, that not always refraction but sometimes reflection also gives us polarized light. So what happens is, if we are sending unpolarized light and it's refracting from a material which has refractive index higher than air, then after reflection the light will become polarized. Some part of it is getting refracted, and this doesn't happen for all angles. It happens at particular angle that we call Brewster's angle, at which the light, the angle between reflected light and refracted light becomes 90 degree, and at this particular angle, the reflected light becomes sigma polarized. The refracted is still unpolarized, just to notice, but the reflected light has become polarized, and this angle we can get by tan inverse of refractive index of that material. This is very easy, but this is also a way through which we can get a polarized light, I would say. Then, yeah, so these were the different materials, right? We discussed there are some natural material through which we get polarized light, or through scattering, or reflection, or refraction. Then there was experiment where we were trying to find out the refractive index for O ray, E ray, and the working principle was that through when the prism, the light passes, the refractive index depends on angle of prism and the angle of deviation. So if we are able to find out angle of deviation, then we can find out refractive index for that O ray, or is it, if it's E ray, then E ray. Okay, then we started discussing this polarimeter, that we understood that there is some phenomena or property of some certain material called specific rotation. What happens in this property is, so there is some compounds called chiral chemical compound, and the specific rotation is defined as change in orientation of monochromatic plane polarized light per unit distance concentration product as the light passes through a sample of a compound in solution. If a compound is able to rotate the plane of polarization of plane polarized light, it is called optically active. So what we meant by this? There is unpolarized light. Okay, means electric field component varying in all the directions. Now I am using some Nicol prism or some kind of polarizer. Passing through it, it becomes polarized. Maybe say electric field vector only varying in one direction. Now I am using this unknown material, okay, and if through passing through this material the plane of polarization changes by some angle, say 45 degree here, that means this is optically active material, and depending on if this plane of polarization has rotated to right or left, right now it has rotated to right, if it has rotated to left, okay, then it's called something else like left, that optically active but it's rotating towards left, and this is optically active but right now rotating to right. So these are those kind of materials. They are called optically active, and they are also called polarimeter. This was experiment based on it. We had to find a specific rotation value where the concentration is known. So specific rotation of optically active substance, when we make solution out of it, is defined as rotation of plane polarized monochromatic light of wavelength produced by column of solution of length 1 decimeter, which is 10 centimeter, and containing 1 gram of substance per centimeter cube. Means the concentration of that whatever optically active material solution we are making, the concentration we take is 1 gram per cc, centimeter cube, and then the liquid column we take is 1 decimeter. Through this particularly defined dimension material, when the light is passing, polarized light, then we take its rotation. These values when we put, we get to know the specific rotation value of that material when we made solution out of it. Yeah, so this is the zone plate we were talking about. If you zoom into it, you will see there are different rings where every alternate ring is darkened and the other is transparent. This is what we have discussed. We get to use it as convex lens if we darken the alternate zones. When we had derived those things, then we have started discussing about quantum based things. Just a minute, give me a break. Let me save this. Just yeah. So after all these optics related experiments, we started discussing about photoelectric effect. I mean the experiments related to that I already today's session also I explained how quantum physics field was developing, and then these were the experiments which solidified its base. One of it was photoelectric effect, which were where if we talk about its background from where its laws came. So Planck introduced this fundamental constant h value, we call it Planck's constant in his honor, and the value is 6.626 times 10 to the power minus 34 joule second. Okay, so energy of a particle in quantum physics we take as this multiple of frequency, and from this concept of that energy is made up of wave packets. This concept when Einstein proceeded with, when he was able to explain photoelectric effect, for which he got Nobel Prize, because classical physics could not explain this we had discussed in last week's interactive session in detail. You please watch there, and we had discussed in detail why it could not explain, because for them light is energy is continuous, so as soon as light is incident on a metal the electrons should reject. But when we did the experiment we saw that even if we increase the intensity of light, but we are using the particular energy light, then we could not see the photoelectrons. So those things we had discussed, that why this is happening. And yeah, we had discussed history, and then we had discussed that how Einstein had considered that light that we know, which when we talk about electromagnetic waves, we say it as wave, which is a electric field component, magnetic field component. But when we, from quantum physics, we got to know that it has particle nature as well. So light has wave nature, light has particle nature. In quantum physics, we consider particle nature and say that energy of light is quantized. That's how we started calling this quantum physics, because we talk about quanta, packets. So we said that this has energy packets called photons. Okay, so and the energy is this Planck's constant times the frequency, and that every photon goes interacts with one electron of the metal, and the metal gets ejected if it absorbs that. We had discussed this in detail how these electrons and photons are interacting, so that sometimes with increasing intensity means more number of photons are coming, and they are interacting with more number of electrons, and thus we get more number of photoelectrons. And depending on the energy, the photoelectrons that are ejected, their kinetic energy increases, because they need threshold energy that we had discussed to come out of or break the bond and come out of the metal or the material. But after that, whatever extra energy they have, that is their kinetic energy. This was the setup which was set up to conduct this experiment, and there were various parameters which had their own importance. Then we were discussing about specific charge of electron experiment, which was done by Thomson, and we call it Thomson experiment. So various models were coming to understand what the matter is made up of. Somebody said it's like a plum model where the whole charge, the material is whole and there is charge embedded throughout. Somebody gave some other experiment, and finally Faraday said that there is something known as charge elementary unit existing. Then later J.J. Thomson said that it's like charge is there embedded everywhere. Then Niels Bohr said no, it's not like this. It's around positive core electrons are rotating in discrete quantized energy levels. This was told by Niels Bohr. But Thomson, what he did, he did accept this unit of charge, and he did this experiment to find out the value of charge of electron. So here, this was the experiment that we had discussed, how to find out value of charge from this. And then we had discussed Frank-Hertz experiment, which strengthened the Niels Bohr's theory that electrons are in discrete energy levels. This was very important, very interesting experiment, how they thought of it and what are the kind of result we saw. After this Frank-Hertz experiment, we had discussed Rydberg constant experiment for hydrogen spectra, how we have Lyman, Balmer, Brackett, Parsons, and these are the line series. Okay, so what happens is, again we have nucleus, then n is equal to 1 shell is there, then n is equal to 2 shell is there. Okay, if the light is jumping from here to first, or if it's electron is jumping from second or first or third level to here, due to some reason they were excited, now they are coming back. When they are coming back, there is energy difference. That extra energy they'll give out as some light, as some energy. So the differential energy comes out, and we want to find out the wavelength of that light. So what forms this Lyman series is, when electron jumps from any excited level, any high energy level, to n is equal to 1 shell, then whatever light is coming out, we call it Lyman. Then when electron from higher level is coming down to n is equal to 2 shell, then we call it Balmer. And similarly, Brackett means from higher level the electron is jumping and coming to n is equal to 3. Then we call those series, it could be coming from 4, it could be coming from 5, 6 or infinity. But if it's coming and staying in 3 level, then we call it Brackett line series. Similarly, this is what we have shown here, and this is the formula that Rydberg had given, using which we can find out the wavelength of those lights coming out. So this is, and based on this we had conducted the experiment. So these were all the things that we had discussed in this experimental physics second module. If you guys have any question related to this, you can ask in the discussion forum. We do answers, I think many of it I personally do, and I am still not sure when you guys have your final the hall ticket is not released, so we don't know where will be a center or when will be your exam, as someone was asking, but at least you be prepared. For many of you it will be convenient. I think not everyone will be busy and they will be able to go and attend or take up the exam. So if you have any doubt, you can ask either below whatever these lectures we have uploaded on YouTube, right, for you. So even if you are not able to attend the live sessions, you can go and watch there, and then either you post your answers there, or if you post your answers in discussion forums, whatever we know we'll be able to answer. But I think for your exam, if you just focus on your as I said, on the assignments that you were given this time, and before the assignments we were always solving the questions which were from previous year's course. By previous years I mean previous year when the same course was kept, that time whatever the questions were given for assignment, so those we were solving in these interactive sessions. And also I was adding some extra questions if I feel it was important. And then apart from all these PPTs in PDF form that I was putting in Google Drive, sometimes also if I found some important separate PDFs, like based on some experiment which has some good explanation. Like I said, I had put regarding significant figures concept. There is a chapter PDF I had kept from NCERT textbook. That is, I think, if you read it once, it will be very clear for once and for all. So these are the things if you keep in mind, I think, and these are the assignment questions that you have done. Then, yeah, one more mistake that tends to happen. So even if we put understand, we make the figures, we understand everything, but one mistake happens is when you about unit. So if some value is given in some other unit, like something, uh, this also we should keep in mind about conversion. Otherwise, it will waste a lot of time when our answer will be not matching in the given options, or even if it's matching, we may be choosing the wrong. I'm just looking for a blank. Blank. Oh, oh shit. Sorry. Yeah, so what I was saying, like you have to keep in mind, if in case, like, see, just say I'm using this formula itself, lens maker or mirror formula. If u is in centimeter, given at 10 centimeter, v given in meter, 0.1 meter or something, I have to keep in mind before calculating f, whatever values I'm going to do the arithmetic with, everything which has, if all the length should have same unit, all the volume has same unit, should have same unit. Of course, I mean, if something is weight, then it will be in kg or something. If something is in length, it will be in meter. But I mean, they cannot have same unit. But if I'm talking about some measurement, then it should be in meter or centimeter. Then everything should be in centimeter. And at the end, depending on if the options have the answer in meter or centimeter or micrometer, accordingly you change at the end. But when you doing the maths, don't keep one thing in centimeter, another in micrometer or meter. Then the answer will be wrong, completely wrong. It will be way away from the correct answer. So that is one thing you should keep in mind. Another thing that may go wrong and you have to keep in mind is something like, if the information is given about that center of curvature or the diameter of uh, the lens which has been cut from the sphere, the diameter was 10 centimeter. That means they are giving us 2f, because focal length is half of it. They are giving information about 2f. So when you are using f or focal length in the formula, you have to keep in mind to take half of it. So these are the places where there is chances of me making mistake more, because if you remember the formula and you go with the procedure, you will be able to do. But these are specific places where you should pay attention. Otherwise, what happens, even the wrong answer, you'll find an option and you'll take it. You'll think, you'll do all the, you'll be following all the method, you will put all your understanding in place, but just because of the small mistake, your answer will go wrong. So this is another thing that you should really keep in mind. And apart from this, nothing else is coming to my mind. I think you'll be able to, yeah, I think this optics and these things, you will be able to uh, solve this. And just a minute. So you have to keep in mind all these formulas which may come. They may ask unit, they may ask just, they may give directly questions, and based on the formula they may ask you to, there may be direct questions sometimes, like we were solving assignment questions, previous year assignment questions. We were seeing that either the questions may be direct, that they are giving you by, like for example, this voltage value, magnetic field value, this constant, and you have to just find out the specific charge. Okay, sometime they may give some 2-3 different cases, and depending on those 2-3 cases you have to uh, get two equations, and then you have to find some information using those two equations, right? So that also you have to keep in mind. We had done various questions based on that also. So I don't think there would be any question depending on the history, because that is difficult to remember. This is just for information. This was a way to show how physics has evolved throughout this time. What was the first hypothesis, then how it evolved, and what were the challenges. As I said, we call it hypothesis until we prove it experimentally, right? So, but as we get some hypothesis, we try to prove it, and if something we see is violating the rule, then we evolve it to something else. Like as I said, right, when this understanding of how the atom is, it started with Thomson saying that so we have atom something like this, and electron is like embedded on it, like like a raisin in pie. But then somebody came and said, after doing Rutherford experiment, I think, if I'm not wrong, they did some experiment in which atom was, they are hitting it by some very highly energetic new neutrons. So what was happening, most of the deviation was happening from the center only. Apart from that, then they got to know that the mass of the atom is concentrated mostly at the center, and the other volume is mostly empty. So they did this experiment, then they got to know that no, the charge is not uniformly distributed throughout in the atom, it's concentrated at the center itself. This was one experiment. Then after this they did some experiment, and then Niels Bohr said, right, that electron, when they were saying, okay, somebody said electron may be revolving around neutron, but then the question came, if it's revolving around, then what will happen is ultimately the electron will fall in the positive nucleus, then the atom will not be stable. So then Niels Bohr gave the concept that no, it's not spiral, it's discrete circular energy levels are there, and electron is there in this distinguished level, and even angular momentum is said that is quantized. So this is how usually physics goes. So these all historical informations were always given to tell you how the science, how physics has evolved. But I highly doubt that you will be asked this kind of questions. Although the basic things like photoelectric effect was given by Einstein, these are the usual thing. If we are talking about photoelectric effect, then we should know that it was given, explained by Einstein. So these are the basic things that we should keep in mind. But basically that's why I'm saying, I think if you are able to solve the questions, the assignment questions, then you will not have any problem. In the assignment questions, you must have seen we were not doing any questions based on history or anything, right? So that's why I'm saying it was only for understanding, but the questions will be numerical or understanding based. That, like, when we are not having numerical questions, then what kind of questions we will be doing? Like, if the object is placed in between the center of curvature and focus, and we are using a concave mirror, then where will the image will be formed? So these are the places where you need to keep in mind that there no formula you will be using, but you need to remember that, like here I have kept a chart, right, that depending on the position of the object in front of concave mirror, where the image will be getting formed. These are the things you should, okay, these are the things you will have to keep in mind, where no direct formula we have, but it's just, especially if you use this two-ray thing, that also helps many time actually. That if we have some object here, and how we take two-ray concept. If one light is going parallel, it's reflecting, it coming out from focus. If one light is going through focus, it will come out from here. So depending on it, we were making, okay, the object will be formed here or somewhere. So that also we had discussed in detail. So any other question if you guys have related to anything? We had discussed in one of the class sign convention thoroughly. That is very important before you attempt any question based on Lensmaker formula. That is very important. had done several questions based on reflection also. Yeah, this is what I was talking about. That these are certain things, if you keep in mind, then if direct questions, MCQ questions based on this is there, then you can be quick in that. Other than that, yeah, I think you may surely get questions based on this thing. So please keep in mind all these rules that we discussed today again, based on these significant figures and what, depending on what arithmetic we are doing with those two numbers, how much the final answer should, how many significant figures or how many decimal digits that final answer should have, right? And again, these are the various rules to tell. I think in first or second week's assignment, we had done several questions based on this. That if you want to just quick revision, then when we define significant figures, so all non-zero digits are significant. Like a number is 1, 2, 3, 4. These are all non-zero. That means this number has, this number, that means this number is 5 significant figures, because all non-zero digits, be they come after decimal or they come before decimal, they all are significant numbers. Now all the zeros between non-zero digits are significant. If I have a number 203, this is significant, this is significant. Just now we said all non-zero digits are significant. So if a zero is coming between two significant, two non-zero digit, then they are also significant numbers. This will also become significant. There's 203. If this digit is not here, it will be 23. So it also has significant place. So this is one rule. Then if number is less than 1, zeros on the right of decimal point but to the left of first non-zero digit are not significant. What it's saying is, if a number is less than 1 and 0 on the right of decimal point but to the left of first non-zero right of decimal point but to the left of first non-zero digit are not significant. So if you have a number like this, when we write like this, it means there is a 0 here, of course. So if you have a number like this, then how many significant digits? 2 significant digits. Why? Because this 0 is not significant. Why? Because you can write it like this also. In scientific notation, when you will write it as 3.5 10 to the power minus 2. This is scientific notation. So then here you see how many significant figures are there? 2. That is why we are saying, because in any notation when we are writing a number, its number of significant figures should not change. Like if I am writing 123 meter and if I am writing as in centimeter, I will get 2 extra zeros. But here there were 3 significant figures, here also there are 3 significant figures. If I write this in millimeter, here also only 3 significant figures are there. These zeros are non-significant. Okay, so the same thing if you write it in notation, scientific notation. In scientific notation, what we do, we write decimal after first digit, right? So if I write, it will be 1.23, and if I want to write in meters, then it will be 10 to the power 2 meters. If I am writing it in centimeter, again 1.23 and 10 to the power 1, 2, 3, 4, 10 to the power 4 centimeter. But while counting significant figures, you don't need to think about these powers and exponents. You just focus here. Yeah, actually this reminds me. This is also could be a question. So maybe based on these rules, you will be able to answer seeing here. But if directly some question like this is given, that tell how many significant digits are in this, 10 to the power, it could be any number. So you don't have to think about this. You just have to focus here. 3 significant figures. You should be clear about this thing. Okay. So yeah, I think if these things are clear and there are no questions, then because today is the last class, so I'll finish this. Okay. Sorry. Getting cold. So, okay, I'll stop the recording. And yeah, all the very best to all of you for your exams. And again, if you have any doubt, either you can put it in the discussion group, or you can ask in under the videos, respective videos. Okay then, bye.